Section: Introduction. In this section, we discuss the impressive abilities of large language models, LLMs, in various complex reasoning tasks, such as mathematics and programming. We recognize that reinforcement learning, RL, has become a valuable method for enhancing the reasoning skills of LLMs by using reward feedback to optimize their performance. Currently, most RL techniques for training LLMs sample multiple responses independently and evaluate them based on their final answers. However, we note that tree search methods, which have been successful in other areas like AlphaZero, have not been fully utilized in LLM reasoning. Previous work has mainly focused on using tree search to improve performance during inference or to generate data for offline training, but these approaches face challenges like distribution shifts and reward hacking. We see that the potential of using on-policy RL training with tree search to enhance LLM reasoning is still largely untapped. There are two main challenges we face. First, traditional Monte Carlo tree search, MCTS, can be less effective than independently sampling responses, as it often results in lower performance under the same inference cost. The step-by-step generation process requires many iterations, which is not ideal for modern LLMs. Second, while tree search can offer detailed supervision, the offline reward models derived from it do not significantly improve RL training performance. To bridge this gap, we propose TreeRL, a new RL approach for LLMs that incorporates tree search. Our method generates more diverse and effective responses while providing on-policy supervision signals to enhance RL performance, all within the same inference cost as independent sampling. We introduce an efficient tree search strategy called EP-tree. Unlike MCTS, which breaks down answers into smaller parts, EP-tree generates new responses by branching from the most uncertain tokens in the existing tree and continues until reaching a final answer. This approach requires fewer tokens and encourages effective exploration, typically needing only about 2 iterations to create generation trees. Furthermore, we utilize tree search for RL with process supervision. Each step in the tree receives a credit based on its advantage, which measures how much that step improves the chances of finding a correct solution compared to others. The process signal for a reasoning step is calculated as a weighted sum of 2 components: global advantage, reflecting the step's overall potential for correctness, and local advantage, measuring the improvement over its parent step. Since these advantage signals come directly from the on-policy generated trees, they are less susceptible to reward hacking and do not depend on additional reward models. We evaluate TreeRL on challenging math and coding benchmarks and find that it outperforms traditional independent sampling methods. The improvements stem from both EP-tree's strong performance and the benefits of process supervision. These findings underscore the promise of combining RL with tree search to enhance the complex reasoning capabilities of LLMs. We have made the implementation of TreeRL available for further exploration. Section Summary. In this section, we discuss the limitations of current reinforcement learning methods for large language models, LLMs, and introduce TreeRL, a novel approach that integrates tree search to enhance LLM reasoning. Our method, utilizing an efficient tree search strategy called EP-tree, generates diverse responses and provides on-policy process supervision, leading to improved performance on complex reasoning tasks compared to traditional sampling methods. Section: TreeRL, Reinforcement Learning with Tree Search. In this section, we introduce TreeRL, which enhances the reasoning capabilities of large language models, LLMs, through tree search. We begin with an efficient tree search algorithm called EP-tree, which uses token-level uncertainty instead of the traditional Monte Carlo tree search, MCTS. We then explain how we can integrate this tree search into reinforcement learning with process supervision to further boost reasoning abilities. Our goal is to optimize the tree search for reinforcement learning training, focusing on the pass rate metric. This metric assesses how well the algorithm can produce diverse yet correct answers within a set inference budget. We also ensure that our tree search algorithm is efficient and can run in parallel. Unlike traditional MCTS, which requires many iterations and is less efficient for current LLM inference engines, EP-tree is designed to be more effective. The main idea behind EP-tree is to expand the search tree by creating new branches from the most uncertain tokens, as determined by their entropy. This approach encourages exploration in areas where the model is less certain, leading to better performance. EP-tree can generate multiple trees simultaneously and only needs about 2 iterations to create a diverse and informative tree, making it very efficient. The algorithm follows these steps. 1. Initialization. We start by creating multiple trees in parallel. For a given prompt, we generate several responses to initialize each tree. 2. Forking token selection. We then expand the trees by forking new branches from the tokens that show the highest uncertainty. We measure this uncertainty using cross-entropy, which helps us identify the most informative tokens. We select the top uncertain tokens across the entire tree and avoid tokens near the end of sequences to encourage exploration of different reasoning paths. 3. Expansion. For each selected token, we continue generating responses to form new branches. This process results in a significant number of new tree nodes, which we add to the existing tree structure. We repeat the forking and expansion process for several iterations, leading to a large number of leaves or responses. We refer to this entropy-guided tree search as an M-N-L-T tree, where M is the number of parallel trees, N is the number of forked points per iteration, L is the number of iterations, and T is the branching factor at each forking point. Compared to independent multi-chain sampling, EP-tree can produce a greater variety of responses at the same inference cost, which can enhance reinforcement learning performance by learning from more diverse outputs. Section Summary. In this section, we introduce TreeRL, which enhances large language model, LLM, reasoning through an efficient tree search algorithm called EP-tree, focusing on token-level uncertainty to improve exploration and performance. By utilizing an entropy-guided approach, EP-tree allows for parallel tree generation and rapid expansion, ultimately producing diverse responses that can significantly boost reinforcement learning outcomes. Section: Reinforcement Learning with EP-tree. In this section, we explain how we incorporate EP-tree into reinforcement learning (RL) training. Hierarchical tree structures not only help us find correct paths more effectively but also offer detailed supervision for intermediate steps during training. For process supervision, we estimate the value at each step using Monte Carlo methods. For a specific step, we identify all leaf nodes that descend from it, including the step itself if it is a leaf. The value of this step is calculated as the proportion of correct leaf nodes among its descendants. This value indicates how likely the step is to lead to correct outcomes. We define process supervision for each step based on advantages, which measure how much better a step is compared to others, considering both global and local advantages. The global advantage of a step reflects its potential to yield a correct result compared to the overall correctness of all samples. We assume a virtual root node for all subtrees, where the root's value represents the average correctness of all responses. The global advantage is essentially the normalized value, calculated by adjusting the rewards across all leaf nodes and averaging them for the descendants of the step. The local advantage measures how much better a step is compared to its parent step. If this value is positive, it suggests that the step is more likely to lead to a correct result, indicating that we should encourage it. We combine the global and local advantages to compute the final reward for each step. This approach can be seen as a specific case of generalized advantage estimation, GAI, where we focus on the direct parent and the root node. During training, we generate multiple trees for each prompt using EP-tree. Each leaf node in these trees corresponds to a complete sequence. We assign process supervision signals to each step based on their importance. The sequences extracted from the trees are then used for RL training. To avoid overfitting, we reduce the reward for non-leaf steps since they appear in multiple sequences. In our experiments, we train models based on specific initializations and fine-tune them using public datasets. We explore different hyperparameter combinations to find the best tree search settings for RL while maintaining a consistent inference cost. We compare our proposed TreeRL method with traditional multi-chain sampling, ensuring a fair evaluation by using similar inference budgets. For RL training, we use a rule-based reward system based on the correctness of the final answer. We set specific parameters for learning and sampling, and we evaluate our model's performance using pass rate, which measures the likelihood of generating at least one correct answer among all outputs. We assess our model on various reasoning benchmarks, conducting multiple evaluations to ensure reliability. Section Summary. In this section, we integrate EP-tree into reinforcement learning (RL) training, leveraging hierarchical tree structures for enhanced process supervision and value estimation of nodes based on their potential to lead to correct outcomes. We define global and local advantages to compute rewards for each step, optimizing the training process while ensuring effective evaluation through metrics like pass rate across various reasoning benchmarks. Section: Results of EP-tree. In this section, we present the results of EP-tree. The table shows the overall performance on OmniMath 500 and highlights the trade-off between efficiency and effectiveness across various sampling methods. We find that EP-tree significantly outperforms the baseline multi-chain sampling and the MCTS method at the same inference cost. EP-tree consistently delivers better results across different generation costs, achieving about a 3% higher pass rate compared to multi-chain sampling. When compared to MCTS, EP-tree's advantage increases as the inference cost rises. Next, we discuss the results from our RL training. The table outlines the performance of different sampling strategies in RL training. Notably, TreeRL using EP-tree sampling surpasses traditional multi-chain sampling across various benchmarks. The figure illustrates that while both strategies perform similarly in the early training stages, TreeRL starts to show an advantage around 100 steps and continues to improve. This suggests that TreeRL achieves better prompt efficiency by providing enhanced performance with the same number of training prompts. Overall, these findings highlight the potential of combining tree search and process supervision in RL training. We note that both RL methods show only slight improvements over the SFT baseline, likely because we selected the RL training data based on Quen-2.5-14b, which may be easier for the R1 distilled Quen-2.5-7b model, limiting performance gains. In our ablation study on EP tree sampling, we examined the effects of entropy-based forking. The table shows that EP tree has a better pass rate than random forking with fewer generation tokens, demonstrating its advantages. Both tree sampling strategies outperform multi-chain sampling, showcasing the potential of tree search. We also conduct case studies to analyze the types of tokens selected for forking. By identifying the top 10 tokens that frequently serve as forking points, we find that mathematical operators, logical conjunctions, and transitional terms like since, and, but are often chosen. Notably, the token weight appears frequently, as models similar to O1 often use it for self-reflection steps. We then evaluate the effectiveness of process supervision in TreeRL by comparing different designs of process supervision signals. Since TreeRL uses more traces than RL with multi-chain sampling, we also assess how the increased training cost affects performance. The results indicate that RL with reweighted local and global advantage achieves the best performance, and removing either component leads to a decline in results. Additionally, using a subset of sampled responses shows less improvement than utilizing the entire set, suggesting that tree search enhances RL performance by allowing more training within the same inference cost. Regarding RL for LLM reasoning, recent advancements have shown the effectiveness of reinforcement learning in aligning and reasoning with LLMs. Most existing methods train a reward model or use rule-based rewards for the entire response. Process supervision has proven to be more effective than outcome supervision. Many studies focus on training a process reward model based on human or auto-annotated signals and apply a static PRM for RL training. However, A static PRM can face issues like distribution shift and reward hacking as RL training progresses. Some approaches address this by using Monte Carlo rollouts to estimate the value for each step, but this method incurs high computational costs, hindering scalability. Tree search has primarily been explored in LLM alignment and inference, particularly for data synthesis and offline preference training. Some studies use MCTS to generate step-level preference pairs for DPO, while others employ MCTS to create high-quality SFT data or process supervision signals for training. However, few have investigated how to explicitly integrate tree search into reinforcement learning training, like AlphaZero, to enhance LLM reasoning. The integration of tree search methods into large language models has shown benefits for both inference and training. Several studies have demonstrated the effectiveness of tree search techniques at test time. For instance, methods implementing tree of thought with depth-first and breadth-first searches, as well as those using MCTS, have shown that tree search enhances decision-making by exploring multiple reasoning paths. Additionally, combining large language models with process reward-guided tree search has improved complex reasoning capabilities. Reward model-guided inference time tree search methods, such as beam search and look-ahead search, have also proven to be efficient test time scaling techniques, often outperforming parameter scaling methods. Recent studies have shown that employing tree search mechanisms can yield high-quality supervisory signals that significantly enhance the performance of language models during training. For example, some research utilizes MCTS to generate step-level preference pairs for preference learning in the decision process optimization stage. Other studies have used tree searches to iteratively train policy value models, where the policy model learns from high-quality sequences generated by MCTS, while the value model is trained on both positive and negative examples. These tree search methods have emerged as effective self-training techniques that reduce annotation costs by autonomously generating high-quality supervisory signals. Collectively, these studies highlight the potential of tree search algorithms in improving the quality of training data for large language models. However, none have explicitly applied tree search within the context of reinforcement learning training procedures. Section Summary. In this section, we demonstrate that EP-tree significantly outperforms traditional multi-chain and MCTS sampling methods in terms of efficiency and effectiveness across various benchmarks, particularly in RL training where it enhances prompt efficiency. Our findings also highlight the advantages of integrating tree search and process supervision into RL training, leading to improved performance and better utilization of training data. Section: Process Supervision. In this section, we discuss recent advancements in process supervision, which have shown promising results. We find that process reward models, or PRMs, outperform traditional outcome reward models, or ORMs, in various scenarios, including best-of-N performance and providing reinforcement learning guidance. However, implementing PRMs comes with high annotation costs since we need to label the correctness of each step carefully. To address this, we have developed automated labeling methods that estimate the value of current steps based on their likelihood of leading to future success. Some studies also look into integrating process supervision signals into reinforcement learning training. For instance, we use PRMs as the supervision signal in reinforcement learning, achieving slight performance improvements over ORMs. Additionally, we combine advantage estimation, which measures progress, with value approximation to enhance both test time search and reinforcement learning. To tackle the problem of inaccurate credit assignment by PRMs, we suggest using unbiased Monte Carlo-based estimates as supervision signals instead. However, this approach faces challenges in efficiency and scalability due to the segments of rollouts that are discarded.